Let's try an indeterminate product. Indeterminate product. Try something like the limit as x approaches infinity, x to the 3 halves times sine of 1 on x. All right. As x approaches infinity, x to the 3 halves power approaches infinity. Right? And inside the sine function, this argument is approaching 0, right? Because the bottom is growing without bound, the top is fixed, so the argument is approaching 0. But sine of 0 would be 0. So this is an infinity times 0 indeterminate product. So we don't know what's going on, and we should try to apply L'Hopital's rule. But to do that, we need an indeterminate quotient. So the usual way to deal with that is to take one of the two factors and rewrite that factor in the denominator. So I can't just put x to the 3 halves in the denominator as it stands, although that is the one I'm going to choose. What I can do is write it as 1 over x to the 3 halves. I couldn't just push the x 3 halves down there. It wouldn't be the same expression, but this is certainly the same as the first. It looks more complicated, it's true, but again, it's just designed to get us that indeterminate quotient. So let's make sure it is an indeterminate quotient right now. As x approaches infinity, we said this factor would up here was approaching 0. It still is, nothing can change that. But this one now, that I've rewritten it as 1 over x to 3 halves, it's also approaching 0, right? As the bottom approaches infinity, the 1 over that is approaching 0. So this is now a 0 over 0 case, and I can apply L'Hopital's rule. So we should have, in exchange for this, the derivatives of the numerator and denominator. The derivative of sine 1 on x should be outer function sine gets differentiated to become cosine. The 1 on x inner function stays the same, and then I take the derivative of the inner function to get negative 1 on x squared. So there's the numerator's derivative. The denominator's derivative, you can deal with it a couple different ways. Let's just view it right now. We'll view this through the lens of being x to the negative 3 halves. Okay? When we do that, we'll use a power rule to get its derivative. So negative 3 halves x to the negative 5 halves. Okay, so I rewrote this, instead of writing this as x to the negative 3 halves initially, I rewrote it as 1 over x to the 3 halves just to show as carefully as possible that this was approaching 0 at this point. Right? And I'm just reusing the negative exponent idea to take care of the derivative itself. Okay? So I'm going to rewrite this now that I've got the derivative handled. I'm going to rewrite this as x to the 5 halves in a denominator. Right? So we'll have, algebraically speaking, no L'Hopital's rule, just through a little bit of algebra here, we'll have limit as x approaches infinity of negative 1 on x squared cos 1 on x over negative 3 on 2x to the 5 halves. All right, so now what I want to do is I want to rewrite this as a single quotient, not as a quotient over a quotient. So we'll get the limit as x approaches infinity. So the 3 halves in the bottom becomes a 2/3 above, and the negatives will cancel, and these powers of x's will cancel to some degree. Okay, so let's see how it turns out. So we should end up with a 2 in the numerator, x to the 5 halves in the numerator, cos 1 on x, and the denominator will have a 3 and an x squared. Okay, so we haven't canceled the powers of x yet. Let's go ahead and do that now. Cancel the powers of x. X to the 5 halves, where x squared is, of course, x to the 1/2. Okay. So we'll now have the limit as x approaches infinity of 2 root x, or x to the 1/2, or cos 1 on x, over 3. This 2/3 could be taken to the outside. It's not that big a deal. Let's just see what's happening now. As x approaches infinity, certainly x to the 1/2, right, the root of x is approaching infinity. The root is not going to curb the infinite growth of x. And what's going on with the cos function, though? Is this still an indeterminate product between these two or not? This is infinite. If this is 0, we'd have to try to use L'Hopital's rule again. But if we look at it carefully here, as x approaches infinity, 1 on x is approaching 0, but cos of 0, unlike the sine function, cos of 0 is 1. So this is not infinity times 0. It ends up being infinity times 1, which is certainly understood as being infinite back again. And since all the quantities here are positive, we now know the answer is infinite. So again, infinity times 1 is still infinite. 2/3 is not going to back down that infinite growth, so we have our answer.